So finally, we have already solved the equation for this line in the graph of the current. And now we could determine the voltage with respect to this line. So the voltage across the inductor, is equal to, we have 5 millihenry times derivative of this current equation. We have negative 20 plus 30 milliamperes, and this results to, we have 5e minus 3 times 10. Okay, that's 0.05 volts, or equivalently this is equal to 50 millivolts. And for the third ordered pair, we have these 2 points. I'm referring to this line. And since we have a straight line referring to the 10 milliampere, that means the current at t equals, that's 3 milliseconds to, at 2 milliseconds up to 3 milliseconds. The equation for the current in this time interval is equal to, we have 10 milliamperes. Since we have a constant value for the current at 2 to 3 milliseconds, therefore we can conclude that the voltage across the inductor at this instance is 0, since we have a constant current. And finally, at time equals 3 to 4 milliseconds, I'm referring to this line, and the involved ordered pairs are 4, 0, and 3, 10. So the equation of the current in this line segment is equal to I of t equals the slope. We have 0 minus 10 all over 4 minus 3 times t plus the y-intercept. So I of t equals, we have negative 10, tama, plus b. And to solve for the y-intercept b, let's recognize at 310 at this ordered pair. And so the equation is, we have 10 equals negative 10 times 3 plus b, so b equals 30 plus 10, that's 40. And so the voltage, the line equation, the current IT equals negative 10t plus 40. And so we could determine the voltage. We have V of t times 5 millihenries times derivative of this current. We have negative 10 plus 40. And so V of t is equal to, that's the same with this equation for the voltage, that is equal to, by this time it is negative. It's negative 0.05 volts, or negative 50 millivolts. And since we are going to compute for the waveform of the voltage inductor, that means that we have to plot these equations. So what are those equations? We have this equation, and this equation, as well as this one. So let's graph this 4 equations of the voltage. So let's draw our Cartesian coordinate system. And in these four equations, we have 50 millivolts and 10 millivolts as peak values of voltages. We have 50 millivolts and 100 and negative 50. So the y-axis, that's for the voltage, and the unit is in terms of millivolts. And for the x-axis, we have the time, the axis for the time. 1, 2, 3, 4. 1, 2, 3, 4. That's too narrow, but it's okay. So the first equation we have, where is it? This one. 100 millivolts at 0 to 1 second. So at 0 to 1 second, we have 100 millivolts. So we have this line graph. And at 1 to 2 seconds, we have this equation for the voltage. So that's positive 50. Wait a minute. This must be negative, since we have a negative sign here. So this is negative. So the voltage equation at 1 to 2 seconds, it's negative 50. So we have this line graph. And the third, we have, okay, where are we now? At 2 to 3 milliseconds, that's 0. So 2 to 3 milliseconds, 0. And last one, we have negative 50 for 3 to 4 milliseconds. And there you have it. This is our line graph for the voltage across the inductor. And if you may want to connect each line graph, you may use broken lines or solid lines. But in my case, I prefer the broken lines. Okay. Or it may look like this if you choose a solid lines, as what most book used to do. And there you have it, the line graph of the voltage across the inductor. So thanks for watching.